We're happy to have Meena Jagadeesan presenting at our ANC seminar today. Meena is currently a grad student in the Berkeley AI Research Lab, where she is advised by professors Moritz Hart, Michael Jordan, and Jacob Steinhardt. She's broadly interested in the theoretical foundations of machine learning and algorithms, including its intersections with economics. And today she'll be talking about inductive bias of multi-channel linear convolutional networks with bounded weight norm. And here's Meena.
Thanks for the introduction. So this is joint work with Ilya Rosenstein and Surya Gunasekar. Okay, so sort of when thinking about a neural network, the easiest notion of complexity is to look at the number of parameters in the network. So while this intuition works reasonably for underparameterized networks, it sort of starts to break down for overparameterized networks where the number of parameters is much larger than the number of samples. So it turns out a much more natural notion of complexity, in this case, is the size of the weights of the network. And the importance of the size of the weights of a network relative to the number of parameters in the network traces back to observations from the 90s by Peter Bartlett. And sort of the intuition here is that the weight norm, or the size of the weights, captures complexity much better than the number of parameters or number of neurons in the network. So in this work, our goal is to study the induced bias of the weight norm of linear convolutional neural networks. So I'll talk about what induced bias means a bit later in the talk, but I'll note now that we focus on the L2 norm of the weights. And this is sort of because it's a simple norm, and also because it arises in the study of neural networks in many applications. So for example, let's consider the explicit regularization. So one of the most common techniques for explicit regularization is weight decay. And this sort of reduces and controls the size of the weight sort of within the optimization algorithm. And weight decay sort of leads directly to controlling the L2 norm of the weights of the network. So another place where the L2 norm of the weights of the network shows up is in the study of implicit regularization. So this basically gradient descent leads to solutions that have certain properties, and these turn out to be closely connected to the L2 norm of the weights. And I'll discuss this application in more detail in a moment. And lastly, I'll just note that the L2 norm of the weights arises in some generalization bounds. First, those in Bartlett's original paper and also in subsequent work. Oh, also I should say, please feel free to ask questions at any point during the talk. Okay, so let's look a little bit more closely at the implicit bias of gradient descent. So consider an overparameterized network. So this is where the number of parameters is much greater than the number of samples and sort of captures many modern neural networks. And let's say that we train this on a binary classification data set. So what makes overparameterized networks stand out is that there can be infinitely many global minima. And basically, in the case of like a separable data set, this can correspond to infinitely many solutions with training loss 0. So kind of a natural question to ask here is, which solution does gradient descent end up converging to? If we know gradient descent converges to a solution with training loss 0, we don't know which solution it converges to. And there is sort of a line of work trying to understand this question. And one salient result is that gradient descent under some assumptions for homogeneous model classes converges to a stationary point of the following optimization problem. So this is basically minimizing the L2 norm of the weights subject to the margin being 1. And so what is this telling us? It's kind of telling us that in parameter space, gradient descent is somehow closely related to controlling the L2 norm of the weights of the network. So this is, I will note, this is sort of convergence in direction. So this viewpoint sort of tells us about what's going on in parameter space. And so like the idea of controlling the L2 norm of the weights tells us sort of something about the weights of the neural network, but it doesn't exactly tell us the properties of the learned functions. So a natural question to ask is, what does controlling the L2 norm of the weights mean in function space? So this is like highly architecture dependent, since controlling the L2 norm of the weights has different effects for different architectures. So kind of a natural way to get at this question is to look at a representation cost. So this is the minimum L2 norm of weights needed to realize a function using a given network architecture or model class. And just sort of captures, like, so if we fix a function, what is the minimum L2 norm of weights way to arrange the network to express and represent that function. So we call this the induced regularizer of the network. So just to formalize this a little bit, so let's let phi be a network parameterized by weights theta. So the induced regularizer is basically takes as input a function and is defined to be the minimum L2 norm required to realize that function with the network. So for example, if a network expresses all linear maps, then this quantity would be well-defined for all linear functions. And this is like, this quantity is sort of highly dependent on the network architecture. Are there any questions about this definition? And this is going to be one of the core objects we look at in this talk. Okay, great. So far we've sort of talked about this purely as a representation cost. So we've talked about the minimum L2 norm of weights needed to realize a given function with a given network. But now let's make the connection to learning a bit more explicit. So let's say we do some sort of regularized optimization problem and say it takes this form. So maybe we're doing some regularization by the L2 norm of the weights. Then we can interpret this optimization problem in parameter space. And basically the L2 norm of weights term can be replaced with this induced regularizer. So kind of the nice thing about this induced regularizer, it gives us a way of interpreting this optimization problem in parameter space. So I've focused here on connections to explicit regularization, but the implicit regularization optimization problem that I mentioned before can also be expressed in terms of this induced regularizer. So sort of the global minima of these two optimization problems are equivalent. I will mention the caveat that the stationary points are not always equivalent. So earlier in the implicit regularization, we did mention that gradient descent was guaranteed to converge to a stationary point. So this viewpoint might lose information about the stationary points, but certainly provides, is equivalent in terms of global minima. Okay, so let's look at how this induced regularizer behaves for different networks. So as I mentioned, it's like a highly network and architecture dependent quantity. So for fully connected networks, for example, this induced regularizer is equal to the L2 norm of the linear predictor. For linear convolutional neural networks, it's equivalent to, with full dimensional kernels, it's equivalent to the L2 norm of the linear predictor in Fourier space and sort of takes different forms for different kinds of networks. And these are sort of like highly different norms. So the point I want you to take away here is just that it's highly architecture dependent, sort of looks very different across different model classes. So as I said, in this work, we're going to be focusing on convolutional neural networks. So we're going to try to understand what this induced regularizer looks like for convolutional neural networks. So we consider simple linear two-layer networks with one-dimensional outputs. And we'll see that even within this model class, the induced regularizer can already take like a rich, take on like sort of a rich set of different norms. Okay, so just to sort of review what a convolutional neural network looks like, our first layer is the convolutional layer, and we're gonna sort of denote this by R K. This R and R shouldn't be there. It's just like a K by C dimensional matrix, and C is the number of output channels. So first, just think about this with one output channel, then we have like a K dimensional vector as the first layer weights, and the second layer weights is like a D dimensional. That's like the linear layer. So these first dimensional weights are sort of the filter, and then the second dimensional weights are the linear layer, and we see that in terms of the output of the CNN. We take the input, this star denotes convolution, so we convolve it with the filter, and then we do sort of apply the linear layer to this. And having multiple output channels basically is just doing this for sort of C different times. And the output channels can be visualized in this picture by the feature maps that are layered behind the images. Okay, does this notation make sense? Because this is going to be important for the rest of the talk. So U is basically the convolutional layer and V is the linear layer. Okay, so let's talk about what like the induced regularizer looks like for this particular for linear convolutional neural networks. Okay, so the induced linear predictor, first of all, takes this form. So the idea, like the operations I've defined, basically lead to linear maps on the input, and the coefficients of the linear map are denoted as written here. Basically, we take the convolutional layer and we convolve it with the linear layer, and this down arrow is just signifying reversing the order of the like vector entries. That's not super important. And I will say the star here is given by this like cross correlation, which differs from like the signal processing convention. It's just the same sort of up to one reversing of vector entries. Okay, so now we have sort of defined this induced linear predictor. And now let's define the induced regularizer. So what we've seen here is that these two-layer linear convolutional neural networks are all, the functions all correspond to linear maps. It sort of turns out that we can express all linear maps in this way, even when there's only one output channel. So the natural way to think about the induced regularizer is taking as input a linear map and sort of looking at the minimum L2 norm of weights needed to realize that linear map. And so the induced regularizer takes the following form. So W here is going to be a d-dimensional vector since the inputs X were d-dimensional vectors. Okay, so this basically the second term is saying that U convolved with V needs to be equal to the linear map, and the first term is looking at the L2 norm of the weights. Okay, so we're also going to consider the induced regularizer for multi-channel inputs, but for now, and for this talk, we're mostly going to focus on single channel inputs. Okay, so what do we show? Well, for single channel inputs, sort of our main contribution is showing that this induced regularizer can be expressed as an SDP. And we show tightness of an SDP relaxation that's independent of the number of output channels. And this sort of uncovers several structural properties of the induced regularizer. We also sort of generalize these findings to multi-channel inputs, although here realizing all linear functions can require more than one output channel. So there is some dependence of the induced regularizer on the number of output channels. And then we also validate our findings for gradient descent. So try to make that connection to the implicit bias of gradient descent more explicit. So I will mention that sort of understanding the induced regularizer is also of importance more generally, for example, in the explicit regularization bounds and potentially some generalization bounds. So so for this talk, we're mostly going to focus on the single channel inputs, and sort of the main takeaway is that we can express this as an SDP that is independent of the number of output channels. So we're going to build up to this result today. Okay, so first let's try to get intuition for what this induced regularizer object really looks like for linear convolutional neural networks. So first let's consider a full dimensional kernel and one output channel. So in this case, like our weights, our first layer weights are d-dimensional, our second layer weights are d-dimensional, and we're looking at the minimum L2 norm of weights such that when we convolve U and V, we get the desired linear predictor W. So because convolutions sort of have a much nicer interpretation in Fourier space, it's natural to just kind of move to Fourier space here, and the L2 norm we know is sort of going to be the same and preserved. So here we get this dot denotes like entry-wise multiplication. So the nice thing is this sort of allows us to think about each entry of the vectors directly. And so now we get this sort of nice form of the induced regularizer. And sort of like with some very straightforward algebra, we can obtain basically obtain the L1 norm in Fourier space of the linear predictor. So kind of what we see here is that the induced regularizer sort of has these sort of relates to this nice norm in the Fourier space, here the L1 norm, and the L1 norm is sort of promoting sparse structures in Fourier space. So what goes wrong? Why can't we just apply this logic to general kernel sizes? So let's even look at the case of, so again, one output channel and a general kernel size. So the thing is, when we move to the Fourier space, we see that we have this constraint on U. So U sort of is required to be k-dimensional. And when we're, just to clarify, when we're convolving, we're sort of implicitly padding U with zeros to make it d-dimensional. And although this is like a subspace constraint, it's not like, doesn't have super nice structure. So it's not totally clear how to deal with this. And so just to give some intuition for the other extreme, let's consider one-dimensional kernels with one output channel. And in this case, this subspace actually has very nice structure. U hat, if U is one-dimensional, it's just like a single constant, and U hat is basically many repetitions of the same parameter. So now we see, since U hat entry-wise product of V hat is W hat, we see that V hat points in the same direction as W hat. Okay, so as a result, the L1 norm, or sorry, the induced regularizer in the case of k equals 1 is equal to the L2 norm of W up to some scaling factors instead of the L1 norm. So these are like very different norms. This in particular doesn't promote any kind of sparse structures in any basis. So the problem is, in general, the constraints on U aren't super, like the constraints on U don't lead to super clean interpretations in the Fourier space. So actually, even for k equals 2, this takes the form of some optimization over these high degree polynomials. And so clean closed form solutions are sort of unlikely to exist. So this whole approach of trying to write down a closed form norm in the Fourier space doesn't really generalize to intermediate kernel sizes. And sort of in practice, we're trying to understand what happens when we have maybe a small-ish kernel size and like what the implicit bias is. And so we can't really get at that through just looking at closed form solutions. Okay, so our approach is basically to build an SDP, like express this induced regularizer as an SDP with a rank constraint, which then we can naturally relax to an SDP. And as I said before, we're going to show this relaxation is tight. So where does this SDP come from? Well, the induced regularizer sort of takes this form. We have this minimum, the same optimization problem as before. So again, U is constrained to be an RK, which is K is the kernel size, and V is a d-dimensional linear layer. And so now let's consider this mixed representation where we write the constraint in the Fourier space, but we keep the rest in the original space. So this allows us to sort of keep the k-dimensional structure of U. So now our goal is basically to express this as an SDP. So let's try to make some like quadratic looking terms emerge. So we can write the objective sort of just directly as these linear functions of UU transpose and VV transpose. And the constraints, so there are these entry-wise constraints on U hat and V hat. And so sort of if we take, for each constraint boils down to sort of one multiplication. And if we take ED to be like the standard basis vectors in D dimensions, we can express this as in like a linear form. And basically now using that the map to Fourier space is linear, this sort of gives us, we can write this as linear in UV transpose, which is sort of the key structural property that we need. So sort of what's going on here, we have these three terms show up: UU transpose, VV transpose, and UV transpose. So now you can kind of imagine what the SDP variable is going to look like. So the SDP variable is basically going to be this matrix, which is UV times, like it should really be U transpose, V transpose here. So this is like this rank 1 matrix. And in particular, it's a rank 1 PSD matrix. And so the key fact is, since U is any vector in Rk and V is any vector in Rd, Z is basically going to be the family of D plus K by D plus K dimensional matrices that are rank 1 and PSD. And so the set of feasible D has this very nice structure. And this is sort of unlike what we were trying to do when we were moving to the Fourier space directly and not able to see this structure. So now we can just basically express the objective and constraints as linear functions of Z. So now you can kind of see where the SDP with the rank constraint is coming from. This induced regularizer is equal to this SDP with this rank 1 constraint, where sort of the linear coefficients are defined appropriately. So right now I've kind of gone through this logic with a focus on single output channels, but I'm going to note that just by changing the rank constraint, you can get the induced regularizer for multiple output channels with the appropriate rank constraint. So of course, to get an SDP, the most natural thing to do is just get rid of the rank constraint. And so this gives us an SDP relaxation of the induced regularizer. Are there any questions about the SDP formulation? Okay, so kind of like the intuition here is Z is really retaining this k-dimensional structure within it. So now like through this variable X. So I'm gonna note that the SDP is dependent on K implicitly through the dimension of Z, but the SDP relaxation is independent of the number of output channels. And this is sort of this key property that we're gonna use to show that the induced regularizer for single channel inputs is independent of the number of output channels. Okay, so kind of our main result for these single channel inputs is that this SDP relaxation is tight. So kind of what we show is for any kernel size, we get this SDP that depends on the kernel size, and we show that it's equal to the induced regularizer regardless of the number of output channels. So what is kind of, before I talk about, give intuition for why this result is true, I'm going to talk about some of its implications connecting back to really thinking about this object as an induced regularizer. So the first is it admits a convex formulation. So this kind of gives us a way to compute it. If we had tried to compute it directly in the original space, it's non-convex and we might get to some local minima. So this is sort of the most straightforward thing we can do. And this allows us to sort of, in particular, compute that bound that showed up in the implicit bias term for any data set. So kind of the main corollary of this result is that the induced regularizer is independent of the number of output channels. So what are the implications of this? Well, it means that the representation cost doesn't actually decrease with the number of output channels. When you add more output channels, it should get easier to, one would think it would get easier to represent these functions, but actually it's constant. And then the second takeaway is it sort of suggests that gradient descent may converge to the same solution regardless of the number of output channels. I'll note that this result sort of doesn't directly imply properties of gradient descent because of the caveats I mentioned before. But it's sort of suggestive that somehow the architectures for single channel inputs with different numbers of output channels may be independent of the number of output channels in terms of their induced bias. Okay, so the second kind of nice structural consequence of this SDP result is that this induced regularizer is a norm in the linear predictor. And this sort of follows from looking at the SDP and showing that the SDP is actually a norm in W. So what does this mean? Let's kind of recall these extreme cases that we talked about before. So we know that when the kernel size is 1, we get the L2 norm in Fourier space of W, which is a basis independent norm. So this is not promoting sparse structure in any basis when we're sort of controlling the L2 norm of the weights of the network. And when the kernel size is full dimensional, we saw it's sort of the L1 norm of the linear predictor. And so this is basis dependent and promotes sparsity in particular in the Fourier space. So we kind of relate, although like these, like at first glance, it would appear that like maybe we get some sort of LP norm for different kernel sizes. That's not really the right interpolation, as we showed with the lack of existence of these closed form formulas. But the SDP, using the SDP, we can sort of bound when this induced regularizer is really corresponding to an L2 norm and when is it corresponding to an L1 norm. And this sort of confirms and suggests this intuition that sparsity in the frequency domain is promoted when the kernel size is large. So kind of the two takeaways that I highlighted here are: one, we get some sort of independence, the number of output channels for the induced regularizer, potentially for gradient descent. And here we get some sort of sparsity in the frequency domain promoted for large kernel sizes. So we actually ran some experiments for simple, like preliminary experiments for gradient descent to like show that these findings appear to hold even for gradient descent, although we didn't prove properties of gradient descent directly. So we trained these two-layer linear convolutional neural networks on MNIST until the training loss is 0. And we computed the resulting linear predictor normalized by the margin, and then we compute the induced regularizer of this predictor, or estimate it in some way. So this is kind of intended to map back to that implicit bias of gradient descent setting. So the intuition was we knew that gradient descent subject to some caveats corresponds to this minimum L2 norm solution that fits the training data. And now we're going to try to use what we've shown about the induced regularizer to infer properties of this solution. Okay, so the first thing that we noted is that their sparse structures are actually promoted in the frequency domain. So recall this was sort of suggested by our results about the induced regularizer. So here we show the linear predictor after training for different kernel size values. These are 28 by 28 images. So the right image corresponds to a full dimensional kernel. The left image corresponds to a one-dimensional kernel. And the top row is just like showing the linear predictors. And then the bottom row is showing the linear predictors in frequency domain. So after we take a Fourier transform. And so the black, I will note in the second photos corresponds to like 0, and the white corresponds to non-zero. So what do we see? Well, at k equals 28, we basically have all black with a couple of white specks. So we get this sparsity in the frequency domain. But for k equals 1, there's basically no sparsity promoted. And we see that even when k equals 3, we're already getting non-trivial sparse structures. And when k equals 9, we're really starting to see some sparsity. Okay, so the second thing that we try to investigate is the induced regularizer really independent of the number of output channels? So this table shows some estimate of the induced regularizer for different kernel sizes as we vary the number of output channels. So here we note that the induced regularizer sort of decreases as the kernel size increases, and that's sort of how the induced regularizer is supposed to behave as the kernel size increases. It gets easier to represent functions. But we see sort of vertically, there is not too much variation in the induced regularizer across different kernel sizes. And these numbers aren't exactly the same because we're training until we get to some training loss, and the induced regularizer sort of continues to decay like indefinitely. But we see there's like some definite pattern of invariance across in each column to the number of output channels. So it suggests that our findings are holding for gradient descent. And so we view one of the contributions of our work as just formulating this testable hypothesis and proving it in a special case. So in the spirit of trying to see if this finding holds for more realistic networks, we just added a ReLU nonlinearity and computed the induced regularizers. So here we don't see as consistent patterns as for the linear networks, but we do still see this sort of general pattern of consistency as the number of output channels increases. And so this is, again, this ReLU experiment is very preliminary, and it would be very interesting to like stress test our hypothesis in different settings, potentially for different nonlinearities or like when looking at more complicated settings. Okay, so thus far we focused on how is there a question? Sorry.
Yeah, sorry, my name is Adit. I had a quick question about this set of experiments. So is initialization at all, like, is there a specific initialization scheme that you're considering when training these linear systems? I mean, is it close to 0, or are you starting kind of with the default?
Yeah, that's a great question. So here in these experiments, we're starting basically close to 0. Sort of the goal of this first set of experiments especially is just to understand when we look at gradient descent, do our findings hold? Because there was this sort of connection to gradient descent that wasn't totally fleshed out. So we just wanted to understand the impact of like really gradient descent here. And it would, so again, I was saying one of our contributions is this testable hypothesis, and it would definitely be very interesting to see if that holds water in like more complicated and realistic experimental setups.
Cool. Thank you.
Okay, so here we focused on independence to the number of output channels for the induced regularizer. But now we're gonna like show a stronger property seems to hold, which is that the linear predictor, so I'm going back to the linear setup, is invariant to the number of output channels. So since there can be sort of many linear predictors that all have the same value of the induced regularizer, this is sort of a stronger statement. So here we show the linear predictors for C equals 1 output channel, 2 output channels, and 4 output channels from top left, top right, and bottom. And we're showing this for the 4 different kernel sizes picked earlier. And we see that these are like visually indistinguishable. So basically it sort of suggests there might be kind of some invariance to the number of output channels, even at the level of the linear predictors. And one thing I want to note is this is kind of the same set of experiments as the ones in the graph, the top part of this graph. And so these like variability, like the slight variability in the induced regularizer sort of is not really shown at the level of the images. So this is suggesting we're sort of converging in the image space. And so these tiny irregularities aren't really important. Okay, so here the takeaway is that the linear predictors appear to be invariant to the number of output channels. And again, it would be very interesting to test this in different kinds of settings. Okay, so I'm going to go into the proof sketch of our theorem. But before that, are there any questions about the setup and the result for single channel inputs?
I actually had one more question. Sorry to bother you again. So just really quick, when the kernel size goes to the full image size, the first, and you only have 1 output channel, this is essentially like doing 2 fully connected layers, right?
Yeah.
So in that case, is that saying like training a 2-layer linear neural network with fully connected layers would induce sparsity in the Fourier transform for the operator? I mean, it's a little puzzling compared to what you would usually get. Yeah.
So that's a really great question. So this is a little bit subtle. So basically we have 2 layers. Yes, they're both fully connected, but we're doing a convolution and then we're doing a linear operator. Let's say that we're in this fully connected case where we're just doing 2 linear layers. So these both express all linear maps, but it's been shown sort of in previous work that the first corresponds to the L2 norm of the linear predictor, and the second corresponds to like the convolutional network corresponds to the L1 norm in Fourier space. So this finding is really about the convolution and the impact of the convolution.
I see. Okay. Okay. And this is like, you're not treating the full kernel size as like, you're still padding and doing convolution with this thing. So it's not exactly equivalent to fully connected in some way. I see.
Yeah, so we're doing circular convolutions in these experiments. So in some sense, it's fully connected.
I see. Okay.
Yeah. And just to like note the circular convolutions here, that's kind of how we're getting this equivalence with like the theory to work with the Fourier space. But yeah, like this is an important point that the intricacies of the network fundamentally affect the induced bias.
I see. Thank you.
And one more thing I'm just going to note here is, so the L1 norm, basically, we're already starting to see non-RKHS norms. So we're already, even for this full dimensional kernel, there's sort of this interesting property, like this full dimensional result was shown in previous work, but there's this interesting property that you're already moving away from RKHS norms. So there's sort of a rich collection of properties that this induced regularizer can take. Are there further questions about the results, like the theorem statement for single channel inputs or the experiments?
Just one question. Did you compare? So this is a linear network, right? So this is equivalent to a 1-layer linear network. Is it correct?
In terms of, so it's corresponding to all linear maps, but it's equivalent in terms of the set of functions that can be expressed, but it's different in terms of the the induced regularizer is actually different.
Right. So did you compare in terms of results with the one layer case with the same regularizer but applied to the one layer network?
So not in this set of experiments, but you should be getting, in this case, the L2 norm of the weights as the induced regularizer, and that's sort of been established in previous work. So
I know that. I was just curious which kind of differences you have in the results.
Yeah, so maybe one way to kind of see that is when k equals 1, we get the L2 norm of the induced regularizer. And so like in the left part of every image, we are like, this is really looking at what happens when you're minimizing or look at the stationary points of the L2.
Yeah. And the other question is, when you do stochastic gradient descent, so you typically minimize the norm of each layer separately with weight decay.
Yeah.
So that's different from your regularizer, right?
Yeah. So so here in these experiments, we're just running gradient descent, and we're not like doing weight decay or anything. But different ways of like instantiating the explicit regularizer will sort of control the weights in slightly different ways. So yes, the connection between what we're doing and those particular settings is like not completely direct.
Yeah, especially with RLUs. Yes.
Yeah, exactly. So we're sort of trying to understand this induced regularizer in like the most basic case, which is really just like focusing on the L2 norm of the weights overall. But that's a really good question. Oh, and I will just mention at this point that I focused entirely on single channel inputs, and I'm going to do that for the rest of the talk. But we show some results for multi-channel inputs as well. And here, realizing all linear maps, even when we go to this linear setting, realizing all linear maps can require more than one output channel. And so the induced regularizer does depend on the number of output channels, but we sort of show some weaker form of this STP tightness, suggesting that when the number of output channels is sufficiently large, our findings are generalizing to multi-channel inputs. So kind of the two testable hypotheses here are for single input channels, there should be, we predict some sort of invariance to the number of output channels, and for multi-channel outputs, there is invariance, but it requires the C to be above some threshold. And we think like our results here are sort of very preliminary. The experiments here are very preliminary, and it would be really interesting to like stress test these observations in different settings. Okay, so maybe now we will talk a little bit about the proof sketch of the theorem. So we have this STP that I described earlier. And we basically have this linear map, and then we have these linear constraints. And our theorem is basically that this STP, like getting rid of the rank constraint, does not affect the value of the induced regularizer. And so it suffices to kind of show that there exists a rank 1 optimal solution for this STP. So that's kind of the crux of this proof. So let's just kind of start by writing down the KKT conditions for the STP. So the dual variable here is going to be d-dimensional. It's really, they're 2D constraints. They're 2D real numbers. We're collapsing this to like a d-dimensional complex vector. And we're just going to use this notation, like the capital lambda, to denote like a diagonal matrix with entries lambda along the diagonal. So let's say that we start with an optimal solution, and it's some PSD matrix. So we decompose it as follows. And let's just suppose that we've done this so that UV is full rank. And so the rank of the solution, let's just call it L. So this corresponds to a solution to for the induced regularizer in the case of L output channels. So now we need to show that L output channels actually doesn't beat one output channel here. So we want to get to a rank 1 solution that has the same objective value. Okay, so let me write down the KKT conditions just as a starting point. These just look sort of like the standard KKT conditions for STPs. And the key implication of the KKT conditions is the expression I've written here. So basically interpreting this as this solution to the induced regularizer for L up channels, U with the colon and then L is corresponding to the weights for the L output channel, and V like colon L is basically the weights for the L output channel in the second layer. And what this rearranging the KKT conditions in this way is telling us is that sort of the ratio in the Fourier space between these two sets of weights is constant across all the layers. So we have this sort of nice structural property that holds between U and V across all of the different layers. And lambda here is the dual variable. And this dot thing denotes entry-wise product. Okay. So as a warm-up, let's just show that this actually just directly gives us, shows that Z has rank at most K. So let's take a basis of the column space of U. Now, basically, the structural property sort of tells us how U pairs with V. So we can just like take these vectors where we have U, and then we have this like specific function of U that's kind of corresponding to extracting the V from the above expression. And the implication written at the top here sort of tells us that this spans the column space of UV. So because U is a K, like U is this sort of at most K dimensional, we know that like there are at most K vectors in this basis of this column space. And so this automatically gives us some sort of spanning set for the column space of UV that has at most K vectors. So this automatically gives us the rank of Z is at most K. And so this just means the KKT conditions give us basically for free that every optimal solution has rank at most K. So kind of what's surprising about the theorem is really that you don't need this K. We can construct a rank 1 optimal solution. So that's kind of the crux of what we're going to do here. So, okay, let's start again with this implication about these ratios of these U's and V's in Fourier space. And let's just like plug this into primal feasibility. So we know that when we convolve, like when we evaluate the convolve U and V, we get to the linear predictor. And so we can kind of write this out. We're interpreting this again as a solution for L output channels, and we can just like write this out using primal feasibility. And so our goal is to construct this rank 1 solution that achieves the same objective as the original, like as the solution capital U capital V, and is also like gives us the right linear predictor. Okay, so the idea is basically we can do some rearranging and show that it suffices to show that there exists U that satisfies this equation. So basically U hat conjugate times U is corresponding to U convolved with V viewed in the Fourier space, and we know that needs to equal W. So it kind of suffices to show this expression, and we can evaluate that U that satisfies this expression is going to result in the same objective as capital U and capital V. So this is kind of how we set up U and V. Okay, so this is really taking advantage of the structure of convolutions here in terms of how we need to show this result. So we can write the time space version, and now this starts to look pretty natural. We want U convolved with itself to be equal to the sum of like the appropriate capital U's convolved with themselves. So it kind of suffices to show the following lemma, which is basically that for any vectors A and B, there's some sort of like additive structure of these convolutions. So when we take A and we convolve it with itself, and we take B and convolve it with itself, we get, there exists some vector that's also K-dimensional that is equal to this sum. And so the reason this is like non-trivial is that the base dimension of these convolutions is D, it is not K. So we're padding A with a bunch of zeros, we're padding B with a bunch of zeros, we're doing these convolutions, and we want to show that it's equal to C that's K-dimensional padded with zeros convolved with itself. And this sort of implies the result, the equation above. So this would suffice to show that there exists a rank 1 solution. So kind of the easy case to get intuition is where K equals D. And we kind of already were able to show this case kind of directly. So we anticipate this case looks easier. So in Fourier space, basically this sort of looks like magnitude of A squared plus the magnitude of B squared equals the magnitude of C squared. Here, these are like cross correlation operators, which is where the magnitude is coming in Fourier space. So we can just basically take C to be this square root. This is boiling down to some sort of result about how we can just take a square root, and that's going to give us a suitable vector. So this is very straightforward for k equals d. The lemma is non-trivial for k less than d because we have these constraints on C. We need C to have this k-dimensional structure, and thus we have some constraints on C hat. So this is kind of like going back to the original problem that we talked about at the beginning of the talk. This is where we need to address this condition on C hat. And so basically the proof sketch just kind of boils down to looking at a polynomial multiplication representation of convolutions, and kind of observing that vectors that are of the form C convolved with itself have some special root structure for these polynomials. And then we just kind of need to show that the roots of the polynomial associated with A convolved with A plus B convolved with B have the right structure. So that's kind of how the proof works, and I'll defer the details to the paper. So kind of to summarize at this point, this kind of is the key structural property of the convolutions that we're leveraging to move from this rank K solution to this rank 1 solution. So this kind of gives us the SDP tightness result. Okay, so I'm just going to give a brief overview of our results for multi-channel inputs. So what we do here is we observe that sort of realizing all linear maps can take more than one output channel. So let R be the number of input channels here. Here, what you should have in mind is these RGB channels, for example, for colored images. And we see that the induced regularizer thus cannot be independent of the number of output channels. So the first thing, so what we do here is we formulate sort of a generalized version of the SDP that I described for single channel inputs. And then we can show basically using the KKT conditions that this is tight for C at least RK. This is probably not optimal. For example, this is not the, we know that a stronger result holds even when R equals 1. So we show this kind of partial result. We can't expect SDP tightness in general here because of the first point. So there's some, like we anticipate there's a stronger form of tightness. In particular, we conjecture this holds when C is greater than or equal to R, but we only show this for C greater than or equal to RK for the general case. So we can actually get like better SDP tightness results for K equals 1 and K equals D, so the two extreme cases. And we show that the induced regularizer takes the form of a nuclear norm and an L21 norm. So this is kind of interesting because even when K equals 1, we've now moved away from an RKHS norm. Earlier it was the L2 norm, and now moved to this nuclear norm. So there's fundamentally these richer inductive biases as we increase the number of output channels. And then we have some preliminary experiments validating our results for gradient descent for the multi-channel inputs. Okay, so basically to summarize, we studied the induced bias of the L2 norm in function space, and we constructed this SDP relaxation of the induced regularizer, and we showed tightness of the SDP relaxation for single channel inputs. So this allowed us to conclude that the induced regularizer is independent of the number of output channels for single channel inputs. And then we provide some empirical validation, preliminary empirical validation of our findings for gradient descent, and in particular with this focus on the implicit bias of gradient descent. We partially generalized our results to multi-channel inputs, but as I said, there's this open question remaining about when the multi-channel SDP is really tight. And I will just briefly show the multi-channel SDP here. So we have basically, instead of having like UV and U transpose V transpose as the SDP variable, we have like, we're including like all of the different input channel weights. So really the first layer weights here correspond to this collection of weights for each input channel, and there's one shared matrix V. So we kind of, the SDP is kind of taking that into account and can be written as an appropriate like linear combinations of Z. We get the same type of sort of rank constraint based on the number of output channels. So we kind of show this for C greater than or equal to RK using the KKT conditions directly, and we conjectured that this holds for C greater than or equal to R, which we showed in the case of one single channel inputs, but we conjecture to hold more generally. And so for future work, it would be interesting to improve the SDP tightness results for multi-input channels. Another very interesting direction for future work would be to explore architectural features such as pooling or multiple layers, or things that weren't captured by our simple two-layer linear networks. And lastly, it would be very interesting to have an in-depth empirical investigation of nonlinearities, and also, as asked by the questions, connecting this back to explicit regularization and implicit regularization more directly, since we're just kind of studying the induced regularizer as its own object in this work. All right, thank you.